Hello everyone, I welcome you all for the first PUC practical session. In this session, we will be learning the experiment number 4, spring constant. The aim of this experiment is to find the force constant and effective mass of the helical spring by plotting T square versus M graph using the method of oscillations. Okay, let's look at what are the apparatus required for this experiment. So the apparatus required are helical spring with a pointer. You can see here, this is a helical spring which is attached to a stand and it has a pointer here. Next, a weight hanger. You can see here, we have a weight hanger with slotted weights. Then a stand with a clamp, and then we need a stopwatch. So here it is a stopwatch. So these are the apparatus required for this experiment. Now we need to understand what is the principle of this experiment. Let us understand it. When a loaded spring is allowed to execute oscillations, the restoring force is directly proportional to the extension in it, and the period of oscillation is given by T equals 2 pi into root of M by K, where M is mass attached to the spring and K is a spring constant. How to understand this one? For example, if I consider a spring, and this is a spring without any load, which means the spring is at its equilibrium position. Say the spring is at the position x equal to 0, which is the initial position, xi equal to 0. Now what we will do is, let us attach some load to the spring. So when I attach the load to the spring, what happens? The spring will be extended like this. Okay? The spring will be extended like this. Means if this is the equilibrium position, after applying the load like this, the spring will be extended so that its new position will be xf, which is equal to some x. Okay? Initially, when the load is not applied or when the load is not attached, the position of the spring is at 0 meter. After applying some load, the spring will be extended and it produces an extension of, say this is some delta x, which is equal to xf minus xi, which is equal to x. Correct? It has produced an extension of delta x. You can see here there is a spring and this is a load. So if I attach some load to the spring, what happens? Yes, you can see the spring will be extended. Okay. Say for example, if I attach a load of mass m, then m into g, that will be the weight of this load, correct? Which is nothing but a force. This weight is nothing but a force. So here, this weight becomes a external force. Okay, this is nothing but an external force which is deforming an object. When we apply this deforming force to the spring, what happens is, inside the spring, it develops a force which is called as a restoring force. Okay, so when we deform this body using an external force of m into g, it produces extension, and internally it develops a force which is known as a restoring force. Okay, if I remove this load, what happens? The spring will get back to its original position again. So the reason for regaining of this original position or original size or shape, the reason for that is nothing but a restoring force. Okay, then what is restoring force? A restoring force is a internal force developed in a spring which tends the body to acquire the original position after removing this load, which is called as a restoring force. The restoring force developed in a spring is always directly proportional to the extension produced in the spring. Okay, the restoring force is proportional to the extension. Now if I remove this proportional sign and write a constant called k, this becomes k into delta x. Correct? Now if I write this equation as k is equal to f divided by delta x, this k is called as a force constant, or which is called as a spring constant. How do you define this force constant or a spring constant? The restoring force developed in a spring per unit extension. This is called as a spring constant or a force constant. Then what must be the unit of this K? See, if F is the force, then Newton is the unit of it, and extension is nothing but meter. Therefore, the unit of spring constant will be Newton per meter. Now, we understood the first part of the principle, correct? The restoring force is directly proportional to the extension. Now, let us understand the second point. If the spring is loaded with some mass, and if I pull this load slightly in the downward direction, and if I release them, what happens now? Now the spring performs a vertical oscillations like this. If I slightly pull this mass in the downward direction, and if I release it, what happens is the spring performs the vertical oscillations like this. Okay, so this is nothing but a vertical oscillation. Time taken for one complete oscillation. What is one complete oscillation? If the spring starts from here, it goes up and coming back to the same position, then it completes one oscillation. Okay, when I pull this load and release it, it performs vertical oscillations, and the time taken for one complete oscillation is known as a time period. So in this equation, they have given what is the time period of the oscillation of this spring. T is equal to 2 pi into root of m by k. This is the time period of oscillation of this spring, loaded spring. So in that equation, T is equal to 2 pi into root of m by k. If I square on both sides, what I will get? T square is equal to 4 pi square into m divided by k, correct? If I square on both sides, we get T square is equal to 4 pi square into m by k. Now, I want this k. How to find this k? K will be equal to 4 pi square into m divided by t square, correct? We get this expression. Now, what is this m? M is nothing but the load or mass attached to this spring. Okay, m is nothing but a mass attached to the spring. And this t is the time period of oscillation of that spring. Now, if I plot a graph of this m versus t square, okay? Plot a graph of m along x-axis and t square along y-axis for the different values of load. What we will get? We'll get a graph like this. This is t square in second square and this load m in kg. So when we plot this graph, how do we get the graph? The graph is like this. Okay. Now for this graph, if I find the slope of this graph, say this is a, b, c. Let us find the slope of this graph. Slope is equal to m, which is equal to AB by BC, correct? This is AB by BC. Now, m is equal to AB by BC. AB is nothing but t square, BC is nothing but m. So, t square by m, correct? So, the slope of this straight line gives us t square by m. But in the formula, we have m by t square, correct? Therefore, this m by t square becomes reciprocal of the slope. Therefore, k will be equal to 4 pi square by m. So, using this equation, we can obtain the spring constant k. Okay, 4 pi square by m, where pi is a constant and m is nothing but the slope of the graph plotted against t square versus m. And here, it is having a negative x-intercept. X-intercept gives us the effective mass of the helical spring. So, this m naught gives the effective mass of the helical spring. It is just the mass of the given spring. That's it. Okay. So, by this method, we can find the spring constant. Now, let me write what is the formula used for finding the spring constant. Well, this is the formula used for this experiment. To find the spring constant, k is equal to 4 pi square by m, where m is the slope of the mass versus t square graph, where t is the time period. Second one, the effective mass of the helical spring. To find this effective mass of the helical spring, we need to find m naught. This m naught is the magnitude of intercept on x-axis. You can look at this graph. So here we have a graph. If we get a straight line like this, which is having a negative x-intercept. Okay. So if I find the value of this intercept, we get the effective mass of the spring. Okay. Fine. Now let us start performing the experiment by taking the readings. Before taking the readings, we need to understand about the apparatus. Yes, you can see this one is a weight hanger which is weighing 50 gram. So if you write this in terms of kg, it will be 0.05 kg. And so this is a slotted weight and which weighs 50 gram again. So I am adding 2 slotted weights to this so that the total mass is equal to 150 gram. Now I am attaching a 150 gram load to the spring such that the spring is extended. Now if I slightly pull this load in the downward direction, if I release it, it performs vertical oscillations. You can see it is performing vertical oscillations. Next, using the stopwatch, we need to count the time taken for 10 oscillations here. So how do you use this stopwatch? That we have to understand first. So here you can see 3 buttons M, S and D. So how do you use the stopwatch? See, initially it is showing the 0 count. To start the stopwatch, press D. And again to stop the stopwatch, again press the D. Now it has stopped. Now to reset the stopwatch, use S. Okay, this is how you have to use the stopwatch. I will tell you again. D to start, D to stop, S to reset. That's it. Now if I pull this spring in the downward direction and allow the spring to oscillate in the vertical direction, so it is performing vertical oscillations. How do you consider one complete oscillation? Now allow the spring to oscillate. Now the lower point is around 24 centimeter. So I should consider that lower point as a reference. Once if it goes up and coming back to the same position, you count that as one oscillation. Okay. So consider lower point as a reference. It goes up and coming back to the same, you consider that as one oscillation. I will show you. See, this is a spring which is performing a vertical oscillations. This is performing a vertical oscillations like this. The pointer is somewhere here. The pointer is somewhere here. If it is performing oscillations like this, consider this point as a reference. Consider this point as a reference. Once the spring goes up and coming back to the same position means it has completed one full cycle or one oscillation. So here you should consider that as one complete oscillation. So once it started from this lower point, goes up and coming back to the same position means it has completed one oscillation. That is how you have to count. So you need to count the time taken for 10 oscillations like this. Once if you switch on the stopwatch, it goes up and comes back to the same position, then you count that as one oscillation. Then again 2, 3, 4, 5, 6, 7, 8, 9, 10. So once it reaches to the lower point again, to take that as complete 10 oscillations. Okay. The initial load is 150 gram. So if you write that in terms of kg, it will be 0.150 kg. So let us tabulate the load M in kg for the first trial as 0.150 kg. Okay. Now in the next column we have time t for 10 oscillations in second. So we need to count the time taken for 10 oscillations in the spring. So we need to take the 3 trials for this. First we will do this trials and then find the mean t of this. What is time period? Time period is a time taken for one oscillation. Here in this mean t, we got the value of time taken for 10 oscillations. To get the time taken for one oscillation, divide this time by 10, you will get the time period. Then square of the time period is written here. First we will finish off this experimental part, then we can go for this calculations. Okay. Now initially let me attach a load of 150 gram. How do you attach the 150 gram load? Now for the first trial, let us attach 150 gram load which is equal to 0.150 kg. So I am adding 2 50 gram slots with a weight hanger. We know that a weight hanger already weighs 50 gram and 2 slotted weights. So 100 plus 50, 150 grams. Okay. Let me add this. Now let us attach this to a spring. Well, now we need to count the time taken for 10 oscillations when the spring is performing the vertical oscillations. First, I will allow the spring to oscillate, just a small pull and release it such that it performs vertical oscillations, and let me now count the time taken for 10 oscillations. I already explained you that how to take the 10 oscillations. You should consider the lower point as a reference. Once it goes up and comes back to the same position, count it as 1. Now I will do this. You just observe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, the time taken will be 7.25 seconds. Let's tabulate this. For the load of 0.150 kg, the first trial, the time taken for 10 oscillations in the first trial is 7.25 seconds. Now let us perform for trial number 2 and trial number 3. For the same load, let us take the 2 more readings, trial 2 and trial 3. Now let us do the second trial. Pull the load slightly and release it. Now it is performing vertical oscillations. Take lower point as a reference and count for 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now the time is 7.09 seconds. For the second trial, this will be 7.09 seconds. Now let us perform the third trial. I will slightly change the oscillations. I am doing the same thing. I am pulling the load and release it. Now it is performing vertical oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for the third trial, the time taken is 7.03 seconds. Now for the next load, the load will be 0.200 kg. We should add 50 more gram. How do you do this? Now I am adding 50 more gram so that the total load will be 200 gram now. If you write that in terms of kg, it will be 0.200 kg. Now let me attach this load. Yes. Now we will be doing the same thing. We should count the time taken for 10 oscillations for this load. Well, so just pull the load and release it. It is performing vertical oscillations. Take a lower point as a reference and start it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now the time taken is 8.16 seconds. Let me tabulate this. This is 8.16 seconds. Now for the same load, let us perform the second trial. Again, we will pull the load. Now the spring is performing vertical oscillations. Count time taken for 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the time taken is 8.22 seconds. Let's tabulate this. This is 8.22 seconds. Now let us perform the third trial. Let's perform the third trial. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The time taken is 8.16 seconds. Fine. Now I will increase the load again by 50 more gram so that the total load now becomes 250 gram or 0.250 kg. Now I have attached 250 gram load to the spring or 0.250 kg. Let us tabulate this. So this will be 0.250 kg. Now we have to perform this one, time taken for 10 oscillations for the 3 trials for this load. Let us do this. Allow the spring to oscillate in vertical direction. Count time taken for 10 oscillations again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the time taken is 9.10 seconds. Let us tabulate this. This is 9.10 seconds. Now let us perform for the same load 2 more trials. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The time taken for the second trial is 9.10 16 seconds. Now for the third trial, the spring is performing vertical oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.03 seconds. Now let me increase the load further by 50 grams so that the total load will be 0.300 kg or 300 grams. Let us add the load, one more slot. Now the total load becomes 300 gram. Let us attach this load to the spring, and now let us find out the time taken for 10 oscillations in this load. Let us count for the first trial. Pull the load slightly and release it. It is performing vertical oscillations. Let's start at a lower point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So exactly 10 seconds. Let me tabulate this. This is 10.0 seconds. Now let us do this for second and third trials. Now for the second trial, do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9.90 seconds. This will be 9.90 seconds. Now the third trial for the same load. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 9.90 seconds. Now let us further load it with 50 grams so that the total load now becomes 350 gram or 0.350 kg. Let us attach this load. Well, now we will be doing for 0.350 kg. Let's find out this column, trial number 1, 2, 3 for time taken for 10 oscillations in this case. Now it is performing vertical oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it took 10.56 seconds. Let me tabulate this. This is 10.56 seconds. Now let us perform this for second and third trials. Allow the spring to oscillate and count the time taken for 10 oscillations. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it will be 10.75 seconds now. Now for the last trial, same load, the trial number 3. Allow the spring to oscillate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10.44 seconds. Now after performing the experiment, you have to remove this load, otherwise the spring may permanently deformed. Okay. So here we have finished the experimental part. Now we are left with a calculation part. So let us do the calculations now. So for the first trial, when the load is 0.150 kg, we got the time taken for 10 oscillations like these 3 trials. Now let us take the mean value of this by adding these 3 divided by 3. 7.25 plus 7.09 plus 7.03 whole divided by 3. What you will get is 7.12. Then here we have time taken for, here we have time period t, which is given by t by 10. You just divide this value by 10. So what you will get is 0.712. Then here we have the square of this time period. So if you square this, what you will get is 0.51 second square. We have finished the first one, correct? We have finished up to t square for the first trial. Now for the second load, the trial 1, 2, 3, the time taken for 10 oscillations for the 3 trials is this. Let us find out the mean value of this. 8.16 plus 8.22 plus 8.16 whole divided by 3. And what you will get is 8.18. And then the period. So divide it by 10, you will get 0.818. And if you square this, what you will get is 0.67. Then let us do for this one. 9.10 plus 9.16 plus 9.03 whole divided by 3. What you will get is 9.09 seconds. Then divide it by 10, you will get 0.909 and square this. What you will get is 0.83 seconds square. Now for this trial, 10 plus 9.90 plus 9.90 whole divided by 3. What you will get is 9.93, and if I divide it by 10, you will get 0.993 and square of this will be 0.99. For the load of 0.350 kg, we got the values of T as this, and mean value of this will be 10.58. And divide it by 10, you will get 1.058 and square of this you will get 1.12. Now we have finished this tabular column, and the next thing is we need to plot a graph of load in x-axis and t square along the y-axis. After plotting the graph, find out the slope, and using the slope you can find out the spring constant as well as effective mass of the helical spring. Okay, let's do this now. Well, this is the tabular column what we have obtained from the experiment. So here we have load m in kg in the second column and t square in second square in the last column. Now we have to plot a graph by taking load m in kg along x-axis and the last column t square in second square along y-axis. Let's plot the graph now. Well, these are the two columns, load m in kg which is along x-axis, which are having the points like this: 0.150, 0.200, 0.250, 0.300 and 0.350. So this will be plotted along x-axis, and t square in second square having a points like this: 0.51, 0.67, 0.83, 0.99, 1.12. So these points are plotted along y-axis. Let's draw the x-axis and y-axis first. This is x-axis and this is y-axis. I told you that along x-axis we have to consider load m in kg. Well, along x-axis for each centimeter the value is 0.050 kg. Therefore here we have 0.050, 0.100, 0.150, 0.200, 0.250, 0.300 and 0.350. Then along y-axis each centimeter value is 0.1 second square. So we have 0.1, 0.2, 0.3, 0.4 up to 1.1 along the y-axis, which are the values of t square in second square. The very important part is to write the scale of this graph. So what is the scale of this graph? You can observe here the scale is like this. X-axis, along x-axis 1 centimeter is taken as 0.050 kg, and in the y-axis 1 centimeter is 0.1 second square. So this is the scale of the graph. Now let us plot the first point. The load in kg is 0.150. The corresponding value of t square is 0.51 second square. Let's plot it. This is the first point we got. For the load of 0.150, the t square is 0.51. Next, the second one is for 0.200, t square is 0.67. So we got the second point. Next, for 0.250, t square is 0.83. This is the third one. Next, for 0.300, t square is 0.99. This is the value. Next, for 0.350, 1.12. Well, so we have plotted all the points now. Now using these points, we have to draw a straight line. Let's draw a straight line S. So we obtain a straight line which is having a x-intercept. Next, we need to find the slope of this straight line. For that, let us draw a right angle triangle. So how do we draw a right angle triangle here? Yes, this is a right angle triangle. Let us mark the points as A, B and C. So ABC is a right angle triangle. How do you find the slope of this now? Slope is given by AB by BC, which is nothing but the length of y-axis divided by length of x-axis. So slope is equal to AB by BC. Now the value of AB is 5.8 centimeter and the value of BC is 3.8 centimeter from the graph. Let's substitute the values. So AB is substituted as 5.8 centimeter, but along the y-axis, if you observe the scale, 1 centimeter value is 0.1 second square. Therefore, you need to multiply the length of AB with 0.1 second square because it is the scale of y-axis. Next, in the same way, BC, the length of BC is 3.8 centimeter. That into the scale of x-axis is 0.050 kg. And now let us do this calculation. The numerator will be 0.58 second square and the denominator is 0.190 kg. And if you divide this, you will get a slope of m is equal to 3.05 second square per kg. So this is the value of slope we got from this line. Okay, fine. Now we have to substitute the value of this slope in the formula for spring constant. Let's do this. Yes, we have a formula for spring constant. K is equal to 4 pi square by m, where m is the slope we have calculated in the previous section. Let's substitute this. 4 into the value of pi is 3.14. We have a square, therefore 3.14 square divided by, in the denominator, m. The value of m is 3.05, which is nothing but a slope. And if you calculate this, in the numerator we have 39.44 and in the denominator we have 3.05. Divide this, you will get the value of K as 12.93 Newton per meter. So this is the value of spring constant we obtained from the calculations. Now we need to find one more quantity, which is nothing but the effective mass of the helical spring. How do you find it? We have a graph here. So in this graph, the line is having a negative x-intercept, correct? It is marked in red color, you can observe here. And let me mark that point as some m naught. That m naught is nothing but the effective mass. How do you find the m naught? M naught is nothing but the magnitude of that intercept. No need to consider the negative sign because mass is always a positive one. Now to find the value of m naught, you just multiply the magnitude of x-intercept into the scale. Here it is. Effective mass m naught equals 0.4, which is a intercept of x-axis into the scale of x-axis is 0.050 kg. If you multiply these two, you will get 0.020 kg. So we got the value of effective mass of the spring. Final part of the experiment is the result. This is the result. The first point is the spring constant of the given helical spring is K is equal to 12.93 Newton per meter, and the second one is the effective mass of the given helical spring is m naught, which is equal to 0.020 kg. That's about the result of this experiment. So by this experiment, we had find the value of the force constant or a spring constant of a given helical spring as well as the effective mass of the spring. That's all for this session. Thank you.